Welcome to the New Technologies in Mathematics seminar of the CMSA at Harvard University. I'm Mike Douglas, and today we're delighted to have Gur-Ari from Google Research to tell us about Minerva, the latest in a series of incredible results of large language models that can answer questions, solve problems, do far more than anybody expected. So it's a very exciting talk. Guy is another string theorist back in the day who moved on to greener pastures. As always, I will offer to take your questions. Either you can ask them or you can put them in the chat, and I will look at your question and either answer it or forward it to the speaker. And then we'll leave several minutes at the end for questions and for perhaps discussion after 3 o'clock. So with that, please, Guy.
Yeah, thanks so much. Thanks for having me. I'm excited to tell you about Minerva, our work on applying language models to quantitative reasoning questions. I'm going to start with some background on transformer-based language models. I assume that many people in the audience don't work on transformers or language models day to day, so I think it'll be useful to give some background on how they work. I won't get too deep into the details. I give kind of a high-level description of what these models are about, how we train them, how we use them, but of course, feel free to stop me with any questions if you want to hear more about these. So that will be in terms of some background. Then the next piece of background will be the role that scale has played in improving the performance of language and other models, other deep learning models across a variety of domains. The message is basically that larger models trained on more data tend to do better in surprising ways. And then we'll get to Minerva and we'll see how all of that can be applied to math and science questions. All right, so let me start with a background, and we'll be focused on transformer-based language models. These are types of deep learning neural networks which have a particular twist in their architecture that makes them very good for sort of sequence-to-sequence tasks, where your input is some kind of text or some other sequence of symbols, and your output is something similar. And so the basic setup is that we're going to have a model that accepts a sequence of tokens as input. And I'm going to use that word a lot, probably tokens. By tokens, I mean, imagine you have a string of, could be natural language, math, code, whatever it is. It's a string of characters. And then we chop it up in some meaningful way into a series of tokens. You can think of it as a kind of compression. We learn how to split it up into tokens, but the end result is that each token corresponds to roughly either a single word or a digit in a number or a particular symbol. You get something that's somewhat meaningful. But roughly speaking, you can think of a sequence of tokens as a series of words and symbols. Then the job of the model is, given this input, to predict the probability distribution over the next token conditioned on all of this input. Namely, the model is asked to predict what it thinks the next token should be given all the input. There are many different setups for these transformer-based models. You don't always have to do this kind of next token prediction task, but that's the setup that we'll focus on here. And the reason is that if you have a model that's pretty good at predicting the next token, then you can do that again and again. And each time you sample the next token, you condition on everything that came before it, including the token that the model itself generated in this sort of autoregressive way. And then you can generate long sequences of text. And so these models become generative models that can, given certain input, can generate some sequence of tokens or words. And the architecture we use to do this, and the word transformer here will basically refer to the architecture. It's a deep network. It's a series of alternating fully connected layers that act on each token. So each token here is going to be represented by some vector, and the fully connected layers act on each token separately. They just act on the vector. So that's one kind of layer. And then the other kind of layer that we have is the attention layer, which is the new trick that's been introduced for these transformer-based architectures. And this allows for basically two-body interactions between different tokens. So that's the layer I'll describe in a bit more detail now. But again, I won't go into the whole mathematical description of how this thing works. I just want to give a flavor of what this attention layer is about. So at a high level, what the attention layer does is for every token, the model needs to output its prediction for what that token should be. So imagine, let's say here we see input tokens, some hidden tokens in the middle of the network, and then output tokens. Let's focus on the last token here, which is going to be the next token. The network is trying to predict what the value is or what the probability distribution is over this token. And now we're doing this as part of an attention layer. So what the network does is it computes a mask over all the tokens that preceded it. So this is going to be a mask where all the weights sum up to 1, so a probability mask over these previous tokens. And then it performs some calculation, which is basically some kind of linear transformation on these masked tokens. So it takes all these tokens, it takes their vector values, it weighs them according to the mask, and then it performs some calculation on them. So the bottom line here is that not only for the last token, but for each token, what the attention layer does is calculates a mask on all the preceding tokens. So we call this a causal mask, and then perform some calculation on them to update the value of the token. So we do this for every token in every attention layer. And by the time we're done with our forward pass, if what we're doing is generating new text, we focus on the value of the last token in the last layer and use that as our next token's prediction. So I hope this is somewhat clear. Feel free to stop me if not. And so that's the basic setup. And so we have two ways of kind of interacting with this model. Once when we're training it, and then when we're using it to do text generation or inference. So the way we train these models is given a sequence of tokens. So let's say this could be a web document or some piece of code that we're trying to train on. We want to ask the model, we want to train the model to do next token prediction, and we do that on every token in the document. So if you think of a sequence of tokens, let's say a piece of code, every prefix of that document becomes input, and then the next token becomes the target for the model. And we do this, we can actually do this in parallel for all the tokens in a document. So every token in a document becomes a target. We calculate the loss on all of these, and then we take a gradient descent step. And this is called autoregressive training because we don't compose a data set of explicit inputs and targets. We do things autoregressively where every document becomes a whole set of samples of inputs and targets. So that's how we train these models. And then after they're trained, to use them to generate text, we again give them some kind of context, let's say a question that we want the model to answer. We use the model to compute the next token distribution. Its output is going to be they're going to be logits and then turned into probabilities. And then we sample from that with temperature. So imagine that the model's output is a probability distribution, PI. We then convert these, we do Boltzmann reweighting of these probabilities with some temperature T that we choose. We get new probabilities and we sample from that to get the next token. And what this temperature does is this is a hyperparameter that we only introduce during inference, and it gives us a trade-off between how accurate the model's predictions are going to be. So the lower the temperature, the more accurate the predictions are, according to the model. The higher the temperature, the less accurate they are, but the more we get more diversity in the text that the model generates. So there's this temperature T introduces some accuracy diversity trade-off into the generated samples. And then once we have this token in hand, if we want to generate more, we add it to the input. Now we have an input that's size n+1, and then we do it again and again and generate a whole sequence of tokens. So that's at a high level how these transformer-based models work. And here's what we've seen when we train these models on lots of data. So essentially, because we don't need data sets that match inputs and targets, we can collect large amounts of data to train these models on simply by scraping the internet. So every web page can basically become a set of samples for training this model. And so we have almost an unlimited amount of data to train these things on. And so we can ask, how does the performance of the models change as we increase the amount of data and as we increase the size of the model? And this is kind of summarized in this plot from nice work by Jared Kaplan and Sam McCandlish and others from OpenAI from a couple of years ago, or say formerly from OpenAI. And what they did is they said, okay, let's take a bunch of different models, let's train them, and let's see how they perform. And the thing that's different about these different models is simply how big they are. So you can make a model bigger by adding layers, by making the layers wider, by doing a few other changes to the hyperparameter. But roughly speaking, you can make a model bigger by changing hyperparameters that give it more parameters. Changing hyperparameters that give the model more tunable parameters. So that's one axis. And then another axis is that you can take each model and train it for longer or shorter. And this is summarized in this x-axis here. This is the amount of compute spent on training a model. So if a model is bigger, it takes more compute at every gradient descent step. And if you train it for longer, it takes more compute as well. So that's the x-axis. The y-axis here is what is the test loss that these models achieved on a held out set of data sampled in the same way from the data set. And so each line here is the training curve for one particular model. The farther right we go, the bigger the model is in terms of lines. And on each line, the more we train, the more compute we spend on it. And we see that the shapes are not too simple. So in the sense that first the model starts training quickly, and then there's this elbow and it starts training more slowly. And that's kind of the typical shape for all of these. But then we can ask, well, for a given amount of compute, what is the best loss we can achieve? And so here comes in this trade-off between model size and how long we trained it for. And we can see that if we draw a line through all these optimal compute points, we find a pretty clear power law. So this is log scale. We get a line that's pretty linear, covers here 8 orders of magnitude. We've seen this hold up for even, we've extrapolated this and we've seen it hold up for more orders of magnitude. So you get a very clean power law behavior, which means that we have predictable improvement in performance as we make models bigger and train them on more data. And so this has become a sort of standard thing to do. You want your models to be better. You don't need to think too hard about it. If you want them to do better on general language tasks, you simply train them for longer, you invest more money, and you get predictably better models. Here, better doesn't obviously correlate to, it's quantitatively better in the terms of test loss, but it's not obvious that this also translates to qualitatively better results just by this metric. But it turns out that it does actually become qualitatively better. And here's another example of this. This is not a language model, but this is from image generation, but we see the same effect. So this is from the party model from Google. We've seen DALL-E from OpenAI, there's Stable Diffusion. So these models, there are different ways of, these are not all the same architecture, but we've seen the same effect basically, which says that the bigger the model, the more we train it, the better the results are. And so this particular example, we see a prompt saying, so the goal with this model is to take a textual prompt and generate an image that corresponds to that prompt. In this case, we have a portrait photo of a kangaroo wearing an orange hoodie and blue sunglasses, standing on the grass in front of the Sydney Opera House, holding a sign that says something. And so we can see how the quality improves as they made the model bigger. So with 350 million parameters, we see that there's something like a kangaroo. It is standing on grass, but it's not really the opera house in the background, and the text is garbled. And then things get progressively better on bigger models. Again, all with the same architecture and the same data set basically, but trained for longer. And then when we get to 20 billion parameters, we see that this is spot on. You get a kangaroo, Sydney Opera House, the text is legible, and everything is as it should be for this image. And so the bottom line is scale buys us predictable quantitative improvement, and also qualitative improvements in many cases.
Guy, I'll ask a question and relay one from the audience. So the loss you plotted was like a cross entropy of predicting the next word? Or,
yes, that's the loss here is cross entropy.
Okay. And then the question is, do you have intuition on what causes this power law curve for optimal loss versus compute?
So there are toy models that essentially say that, well, you can reproduce this behavior on linear models if you have a hierarchy of scales in your spectrum of the kernel. So you can imagine that if you have a task that's, well, I'm going to use the word multi-scale, which sort of has to make an appearance here because this is a power law, right? But here multi-scale refers to something like a task that's composed of many, many different subtasks, each with its own complexity. And if you have a whole hierarchy of scales of such complexities measured by this test loss, then you can imagine that, well, smaller models will pick up on the easier subtasks first. And then as the models become bigger and you throw more compute at them, they get progressively better on the harder and harder tasks. So if you have this kind of power law structure and the complexity of your task, even with linear models, you will reproduce this behavior. This is not, I wouldn't say that this is descriptive. This is not predictive. So we cannot affirmatively say that that's what's going on, but it seems like a plausible description of why this is happening.
Thanks.
Okay, so that's the message on scale. And so what we wanted to do was we said, okay, these models are getting better on a whole different lists of tasks across different domains. We've seen many tasks on natural language where things get better. We've seen models that work well on code. We've seen image generation and many other things. Can we apply the same idea to quantitative reasoning? Language models have traditionally not shown a lot of improvement on quantitative reasoning tasks. So that is something where progress has, if you just take a large language model, train it on general data scraped from the internet, you see some improvement on very simple things like arithmetic, but you don't see a lot of improvement on hard math tasks. And so our question was, well, can we apply scale in a thoughtful way to quantitative reasoning tasks and see whether we can improve capabilities of these models if we do it. So we still want to do something where still we can apply large models with lots of data, but we want to kind of aim our approach toward quantitative reasoning. And what we ended up with was doing the following. We collected a large data set of documents, but ones that are filtered to contain math. So still a fairly general data set, but filtered to kind of push the model toward the area where we wanted to excel. And then we took a large pre-trained model and fine-tuned it on this data set. And finally, with this pre-trained model, it does okay, but we applied a whole bunch of inference time techniques. These are techniques that we already have the weights. We're not touching the weights, but we can do all kinds of things when we sample from the model to improve its performance, which I'll describe. So before going into the whole procedure, I want to give a couple of examples of what we ended up with. What can this model do? And at a high level, this model can solve math and physics questions and other science questions using informal math. At a level that's roughly high school Olympiad, going up to early college. That's kind of the level where this model ended up in. So here's one example from a benchmark called MMLU. This is a large data set of multiple choice questions that contains math, physics, and also many other topics. And so the question here is, we have a uniform solid disk. It starts from rest, it rolls down an inclined plane. After some time, and this is the question, we are asked to calculate the fraction of the rotational kinetic energy over the disk's total kinetic energy. Okay, so asked to calculate some fraction, and these are multiple choice questions. So we are given a few different options for this fraction. And this is what the model, this is what the model's answer is. And so again, the way this is generated is we have this model, we give it the question, plus a few other things in the prompt that I'll describe later. And then we start sampling from it token by token. And so we see these words come up token by token. Each time we have a word, we add it to the input and we keep sampling. This also goes for the math. So the input and the output for this model is all done in LaTeX. And so the way these things show up is they actually, the model's output would actually look something like this. You would get these tokens representing the math that the model is generating, and then we go and render them to show the final answer. And so this is what the model does. It starts by just giving an explanation that this has both translational and rotational kinetic energy, and then it introduces some symbols for the speed and the moment of inertia and so on. And then it starts recalling formulas. It says that the translational kinetic energy is given by this formula, the rotational kinetic energy is given by this formula, and then it plugs in the moment of inertia here, which I admit I had to work through a few times on paper, making sure that this is the right formula for a uniform solid disk, and then simplifies things a bit to get the rotational kinetic energy. And then it says, okay, we have these two things. This is the ratio we're asked to calculate, plugs in the relevant results from earlier, simplifies, gets to 1/3, and then goes back to the multiple choice question and says, okay, so the answer is B because B is 1/3. So that's an example. Here's another example, this time from a different benchmark called math. So this is a math-focused benchmark of Olympiad level high school questions. Again, split up into some topics. This is from intermediate algebra, and this is considered the easiest level in this benchmark. So the question here is find the center of an ellipse with this equation. And so what the model does is it simply writes down the equation and then starts doing the symbolic manipulation needed to simplify it. So it completes the square, moves things around, and then ends up with this formula. Again, this is all generated token by token. It ends up with this equation, and then it reads off the center of the ellipse from this equation. It's -4,1, and then says the final answer is this. And so because the model is a generative model, it's not restricted to multiple choice questions. It can answer these kinds of open-ended questions as well. Okay, so these are a couple of examples kind of illustrating what this model can be expected to do. And now I'll go into more details on how the model was trained and what inference time techniques we used. So the training data set, the size is about 60 gigabytes of documents that contain some mix of natural language, English, and mathematical expressions. It comes from two sources. So one is archive. We have a dump of all the archive papers from about a couple of years ago, I think. And then that's about half the data set. And then the other half is scraped web pages that contain some mathematical expression. So the way you put LaTeX on the web is typically use MathJax or MathML. These are two popular ways of putting LaTeX in a document that then gets rendered if you go to that page. And so we look for pages that have those forms of math in them. So either TeX or ASCII math. That's another popular way of putting math on the web. And we collect a data set of pages that contain math. These are the two criteria for whether a document belongs in this data set or not. And then the next step was to take this information and, well, archive papers we can use almost as is because they're already in LaTeX format. Web pages contain a lot of HTML tags in them. And so we process them such that we remove HTML tags, but we keep the mathematical expressions intact. And so we strip out HTML tags around, but whenever there's LaTeX, we want to keep it intact, not lose any symbols or anything like that. And the goal is explicitly so the model will learn about LaTeX, and so it'll be able to process LaTeX input and produce LaTeX output. So that's the data set. And then to train a model, we started with PaLM, Pathways Language Model, which are actually 3 language models that were trained at Google. They were trained on general language data, again, scraped from the internet, web pages and Wikipedia and other things. There are 3 such models with 8 billion parameters, 62 billion, and largest one with 540 billion parameters. So we took these 3 models and then we fine-tuned them on this technical math data set that we created. The smaller models we trained for a few epochs. The largest model we didn't have enough compute budget to, I think it was trained for even less than 1 epoch because we ran out of chips basically. But to give a sense of how much compute was needed, so for fine-tuning the largest model, this was trained for a month on 1,000 TPUs, which corresponds roughly to 1,000 GPUs. Okay, so that's in terms of details of how the model was trained. And now let me go to how we use this model to produce the answers that I showed before. So if you take these pre-trained models and any of them, and you just ask them a math question like I showed before, you'll get something. Sometimes it will be, the quality might be good, but generally speaking, it won't be great. It won't be at the level of definitely won't be as nice as the examples I showed before. You need to put in some work to sort of elicit these kinds of step-by-step correct solutions out of these models. So there are 3 things that we do at inference time that really help boost performance and get these step-by-step answers out of these models. The first technique is called few-shot prompting. So this was discovered as part of in the GPT-3 paper, where they showed that if you want to ask one of these models a question, one of these language models a question, it really helps to show it some examples of questions and answers before you ask it the question. The examples don't need to be tailored to each particular question, but they need to be kind of in the domain of the question you're going to ask it. And if you do that, that really helps boost performance. So just to be clear, all I mean here is that the input to the model shouldn't just be the question. It should be a list of questions and answers, and then the question that you want to ask. That's going to be the input to the model. So here, for example, this is the prompt that we use when we ask the model to do some arithmetic, and I'll show results on arithmetic later, but this is what we use for any arithmetic question. The next step after that is to use few-shot prompting. But if we just do that on the math questions and we just give the model the final answer, the model will try to, on the harder math questions, will still try to just generate the final answer in one pass, which is very difficult. We can then push the model to try to generate step-by-step solutions for questions by showing it in the prompt examples of step-by-step solutions. And that's called chain of thought prompting. And the idea here is, again, we do few shot, we show the model a few question answer examples, but the answers are going to be step-by-step answers that end up with a final answer for the question. So here's an example from the prompt that we actually use for producing answers to these math questions. Find the domain of this expression, so a fraction of 2 square roots. And this is the solution. This is from the math data set. The solution is the target solution from the math data set. And so we see something like expressions inside each square root must be non-negative. So x minus 2 is greater or equal to 0, and so on and so forth. And so the domain of the expression is 2, 5. And then in the prompt, we put final answer. The final answer is this. I hope it is correct. And the point of doing that, and we give 3 more examples that are like this, randomly sampled from math, and then we ask the question and ask the model to generate the solution. And the point of putting this, I hope it is correct, is the model will imitate this when it's generating an answer. So it will try to generate a step-by-step solution, and it will end with, I hope it is correct. And that's a useful signal for us to know when the model is done answering the question. So we kind of look for, I hope it is correct, and then extract the answer that came before, and then we can automatically evaluate whether the model got it right or not. So that's the second technique. And then the third technique is called majority voting or self-consistency. And the idea here is that as as I mentioned before, these models are stochastic. Whenever we sample from them, if we sample with finite temperature, we will get something different, some different answer. And in fact, these samples are independent. And so we can sample many times from the model, and each time we will get something different. Maybe the final answer will be the same, but the chain of thought that leads to it will generally be different. And it turns out there's signal in those samples that we can use to boost the performance. And so the idea here is pretty simple. We have a question, we prompt with chain of thought and everything, and then we sample from the model multiple times. So imagine, let's say we're sampling 100 different times, and then we are looking for the final answers in all those chain of thought answers, and we're bucketing them. And then we look for the most common final answer and just choose that to be the actual answer from the model. So we don't need to introduce any new information about the question or the domain or anything. We do invest more compute, but it turns out that doing this gives us higher accuracy. So more often than not, in a sense, the model will arrive at the correct final answer. And we will see an ablation later on of how much this technique actually helps. It helps, to us, it was surprising how much doing this helps. All right. Question?
I just, when you, in that procedure, do you lump together textually identical final answers, or do you have some broader notion of equivalence of final answers?
Okay, so we do some processing. Yeah, so that's a question for this, and also for how we evaluate final answers. We do some processing to see to sort of standardize the final answers. So the few things we do are we remove things like commas and currency symbols like $ from numerical answers. We do SymPy simplification of final answers. So this is meant to, for example, you can have square root 1/3, or you can have 1/square root of 3, right? And these are equivalent. So we do SymPy. These things give for example, the SymPy simplification changes the accuracy by like 1%, which means it's a more accurate measurement of accuracy. So we do the same. We do the same in this bucket.
Right. Thanks.
Okay, so let me show a couple more results from the benchmarks, and then I'll show the aggregate performance that the model gets on these two benchmarks, math and MMOU. So again, math is this high school level, Olympiad level math questions. So here's another example of a question. So we have a line that's parallel to this line. It passes through 510. And then what is the y coordinate of the point where this line crosses the y-axis? And so the model, basically what the model does is says, okay, the line is parallel to this, which means that it has the same slope. So it's going to use the slope here, and the line passes through 510. So it writes down the equation, taking the slope and these 2 points into account. Then it goes through simplifying it a bit. And then it says, okay, we need to see where it crosses the y-axis. So we're going to plug in x = 0, simplify, and get -10. So that's another example from math. Here's another example from math. I just want to give a sense of kind of what these questions look like before showing the aggregate results. So here we have a question where, so a particle moves so that it has these coordinates, find the speed of the particle. And what the model does is it says, okay, the speed is a magnitude of the velocity vector. And so we need to find the velocity vector, which is the derivative of the position vector. And so it takes the derivative here of the coordinate vector, calculates the derivative, simplifies a bit, and then goes on to calculate the magnitude. So here's the magnitude, simplifies a bit, uses cosine squared plus sine squared = 1, and gets at the final answer. So these are two examples from the math data set, and here's the performance on math for various models, and going by topic, and then on the right we have the average performance on the whole data set. And so we see a few things here. So the ablations shown here are, we see how performance changes as we started with a bigger model, so Palm 8B, 62B, 540B. So this is sort of going on each bar from left to right, is increasing model size. And then within each model scale, we have the bottom bar is what we have with a pre-trained model with no fine tuning on any math data. So these are let's focus, let's say, on the biggest model, the 540B model. So these are the rightmost bars here. So this is the performance of the baseline model. And then the Minerva model, that's the model after doing some fine tuning. This is all done with chain of thought prompting. Otherwise, everything is much worse. So everything here is with chain of thought. And so you see you get a nice boost in performance from the fine tuning. And then finally, we add the majority voting where we sample multiple times and do the bucketing procedure. And this is the last step here. And you can see that this gives significant improvement that's sometimes comparable to how much we got from fine tuning. So majority voting really helps a lot. And so at the end of the day, for this data set, the best model we have achieved slightly over 50% accuracy on this benchmark, and this is currently the state of the art, at least the published state of the art result for this benchmark.
Do you have a sense of what's the wrong answers look like?
I'll show examples of a few wrong answers and some statistics on what they are. Yeah. Yeah, that's coming up in a few slides. Yeah, because obviously the model is still making a lot of mistakes. We're like nowhere near solving this benchmark yet. Here's the other benchmark, MMLU. This is the multiple choice benchmark. This is I like this example because the model it's kind of cute. I think what's happening here. So it's a physics question. A stone is thrown horizontally with some speed. And then it falls down and we're asked to calculate its final velocity as it enters the water 4 seconds later. And we get these multiple choice. We need to choose among these multiple choice answers. And so the model starts calculating. Since the stone is thrown horizontally, after 4 seconds, it calculates the vertical speed and it uses 9.8 meters per second squared for G. It gets this number, which is not a round number. And then it goes on to calculate the magnitude, and it ends up with this expression, which is not going to end up with a round number. And the reason is kind of at this level, students are expected to probably plug in 10 meters per second squared to get the final answer. So the model kind of says, okay, so this is the number. It's not going to be exactly right, but it's approximately equal to 50 meters per second. So it kind of has to correct itself along the way because it used the more accurate G value, which is something that I'm guessing has happened to folks in the audience as well. And here are the aggregate results on MMLU. This is a more diverse benchmark, so it's not all focused on math. So you get these different, you got engineering, chemistry, math, physics, biology, computer science. There are also other categories which we didn't evaluate on. We focused on the STEM categories in this benchmark. And again, this model gets state-of-the-art results on this benchmark. This is, I would say, an easier benchmark than math, which is why you can see we get up to 70-something% on this, but still it's far from solved. So now to answer the question, here are examples of mistakes the model makes. So I'll give 3 examples and then kind of statistics of what the different kinds of mistakes look like. So there are knowledge mistakes, like in this question, we're asked to figure out or to say what kind of eclipse is it when the shadow of the moon falls on the earth. And the answer is solar eclipse, but the model just says lunar eclipse. So they're like simple knowledge mistakes that the model makes. There are calculation mistakes that the model makes. So here the question is, we have a figure skater that's spinning. We're told how many degrees the spin is, and then we need to say which direction. So starting by facing north, which direction is the answer ending up in? And the answer is incorrect, and it's incorrect because okay, she spins 2250 degrees, which is 5 360-degree rotations and 150 degrees. This is not correct. And I think even if this is correct, it's not going to end up facing south. So there are like basically 2 calculation mistakes here. So final answer is south. That's not true. The correct answer is east. But one point that I want to make here is that this clearly shows the limitation of a model that's been trained on general data and is just asked to generate open-ended solutions to questions. When it gets it right, it's great. But when it gets it wrong, we don't really currently have an automatic way of identifying these mistakes either in the final answer. Of course, let's say we don't know the final answer, but even looking inside the chain of thought and identifying calculation mistakes like this is not trivial, because there's no one format that the model uses to produce these calculations. It can do it in the form of an equation. It can do it just using words like this. We don't have a good automatic way of going in and checking the calculations automatically using some kind of calculator. And so when we end up with a mistake like this, it's just a mistake, and we don't currently have an automatic way of identifying that. So that's, yeah, I think, question?
Yeah, a question from the audience.
Mm-hmm.
Okay,
Yeah.
go ahead.
I can go ahead and ask. So I was wondering, in the results that you showed previously with the bar plots, there were these different ablations, and we could see on most subjects, the result would improve when you add the this majority voting, say. But then, say, biology and computer science, there it seems like, in particular in biology, there is no improvement. There's just like this bar for palm, I think. So any idea or intuition on why on some subjects these tricks do not help improve the result?
I think my guess is, yeah, I think it helps the most when you have a long, intricate chain of thought leading to the answer, because then when you sample multiple times, you really get very diverse answers. When it's like a knowledge question like this is not a biology question, but when there's a simple question like this, where really all you have is either you know it or not, then I don't think majority vote will help. Actually, probably in this kind of case, probably lowering the temperature will do better than majority voting. So yeah, that's a good question. So there's probably like a trade-off here between how intricate the answers are versus how much you can just give an answer immediately. And probably then, I mean, that probably turns into a trade-off between, do you want to do higher temperature with majority voting, or do you want to just lower the temperature and get a more accurate answer?
Yeah, okay, I see. Thanks.
Okay, so we were here. Okay, so there are these calculation mistakes. There are also reasoning or logic mistakes, which are, this is kind of a broader category. It's not some arithmetic mistake that happens. It's a reasoning mistake. It's a mistake in the chain of thought reasoning. Some of the steps are just like incorrect statements. So here's an example of that. So the question is, what is the largest 3-digit number in which the product of the digits is 12? Okay, so the model's answer is the largest 3-digit number is 999. This is true, but completely unhelpful for solving the answer. So far, we haven't gone off the rails yet. And then it goes on to say the prime factorization of 12 is 2 raised to the power of 2 times 3. This is correct. And this is also something that this model really likes to do when solving questions. It really likes, when asked about these kinds of number theory questions, it really likes to take numbers, split them up into, give the prime factorization, and then say something about that to solve the question. And often it works. And the model has learned or memorized the prime factorization of lots of numbers. It does this for like 3-digit numbers, 4-digit numbers. Sometimes it gives a list of like 9 factors and says, oh, there's no 7 in there. So the answer is like this. So this is kind of a, for some reason, a strategy that the model uses a lot for solving questions. But here it doesn't actually work. So this is the prime factorization. And then it says the digit 223 will work. That's not correct. And then it says, but the largest 3-digit number will be obtained by choosing the largest digit for the hundreds place. So it goes on to put 9 there, and then 3, and then 2. So that's just wrong. And then it says this is the final answer. So this is not correct. So already like there is a mistake here, and there's a mistake here, but it's not an arithmetic mistake. It's more like just a reasoning mistake. So these are the common types of mistakes that we see. We also see false positives. So these are examples where the final answer turns out to be correct, but there's a mistake in the chain of thought reasoning. So here's an example. It's a bit intricate. Find the smallest positive integer k, such that for every positive integer n, 6n plus k is relatively prime to these three numbers: 6n plus 3, 6 plus 2, 6n plus 1. Okay, so we're looking for a smallest k that has this relative prime property. And so the model answer starts, the correct answer is 5, and you can kind of see that quickly because if you put k1, 2, or 3, then you just get one of these numbers, so they're not going to be relatively prime. And then if you put 4, you get an even number, which is not going to be relatively prime to this. So 5 is kind of the first thing that could work, and it's actually the correct answer. But what the model does is it says, okay, we have these 3 constraints on the GCD of these 3 numbers. That's so far so good. But then it starts making mistakes. We can cancel out the 6n terms from each of the above expressions, which is not correct because they're inside GCD. And then it doesn't even do that, just cancels them on one side. And then it starts introducing more notation, and it just doesn't make sense beyond this point. But then it says k equal 5 is the smallest integer, which is correct. So this also happens. We looked at, we tried to estimate how often this happens by looking at, I think, like 200 examples, something like that, 100, maybe 200 examples. And the estimate is that this happens in 8% of answers on math. 8% of the answers we get have this false positive property. Okay, overall for the model mistake statistics, we looked at 200 samples where the 8B model got it wrong and the 62B model got it right. And we wanted to see what the mistakes were of the 8B model. And they were roughly half and half between incorrect reasoning and incorrect calculation. And we also identified a few other categories, like recalling an incorrect fact happens sometimes, and a few other things. But the most common mistakes are simply getting a calculation wrong or making some mistake in the chain of thought reasoning. Okay, now a couple of other results, which are, so far we really focused on math and physics questions, trying to generate step-by-step solutions to these. I'll give a couple other examples of what the model can do, because again, we didn't train it specifically to solve math and science questions. It just so happened that after training on this large corpus of math data, including papers and stuff, it ended up being good at that. But we don't actually know the extent of what this model can do. And there can be other capabilities kind of hidden in there that we're not aware of, just like what happened with other language models in the context of general language. And we still I don't think we still know like the full capabilities of the model. So here's a simple example. The model can be, we can try to use it as a calculator, just ask it to solve basic arithmetic questions. And this is with no chain of thought or anything. This is, let me scroll back. This is with this prompt. Just give it question and answers like this. And so when we do that and ask it an arithmetic question, it will just try to generate the answer just like in one go, like multiple passes because there are multiple tokens here, but no step-by-step solution, just a calculator basically. And we see that it ends up being pretty good at that. It can do, for example, addition of 8-digit numbers or 9-digit numbers at above an 80% accuracy. Which I think is the best we've seen a language model do on this. Definitely better than a human without access to kind of pen and paper to work things out using long addition, and does reasonably well on subtraction and reasonably well on multiplication. So over 80% accuracy on like 2 or 3 digit multiplication, but then it's also clear that it's not like the model has figured out how to do long addition and will just apply it correctly to any addition problem we ask it, because the performance does start going down after a certain number of digits. I don't have an explanation of exactly how this works, but just from these results, it's pretty clear that it hasn't like kind of fully learned how to do basic arithmetic. Here's another example of something we noticed that this model can do. It turns out that it can solve some questions that have diagrams in them. the way this works is, this is not how the diagram is presented to the model. The way it's presented is the way the diagram is generated is by using a vector drawing language, like maybe you're familiar with asymptote or TXZ. So these are examples of languages where you write code that includes instructions like draw a line from 0, 0 to 10, 0, draw a line from 0, 0 to like 0, 40 or 30 or something like that. And then a whole bunch of instructions like this to generate the diagram. And that's what the model takes as input. It gets the question and then the code for generating the diagram. But it turns out that the model can actually use the information in the code to solve the question. It must have seen a lot of code like this, at least in archive papers. And it's been enough to solve some of these questions. So you can see here, we have these squares, and the question is, what's the total area of the shaded region? That's the gray region. And so it says, okay, the area of the shaded region is the sum of the areas of the two right triangles. So it notices that these are right triangles. And then it goes on to describe the properties of these triangles and calculate their areas and then sum them up to get 10. Yeah, question?
Another audience question.
Oh, hi, Guy. I was just going to ask, like, is there any way to prompt or force the model to give a longer answer? In case it's like too short, or like maybe it's making a mistake and you just want to see where it's making a mistake.
I mean, you can try to prompt it with longer answers, and maybe I don't know. I don't think we've tried that. You can try prompting it with longer answers, and then maybe it will push it to generating longer answers. But sometimes you want short answers, right? So it's not. I mean, I guess maybe if you do that, you can increase performance on a particular question. But I guess the question is there a general way to do that that would increase performance on average? And that I don't know.
Well, another interpretation of the question, which would presumably just require manual experiment, is if after it produces an answer, can you get it to further explain itself?
Yeah, that should be, I mean, that should be doable with a prompt. So like, I mean, if you give it a prompt and then include explanations following the answer in the prompt, just give it examples of what you want it to do, it will try to do that. To what extent it will help on accuracy, I don't know, but you can try to get it to do that. I think the whole question of what can we, given the model's answers and all the tricks we have, can we reuse the model to improve on them? That's a very interesting question, and something that's, like, I would say, an active area of research right now. Okay, let me see. I think, yeah, I think we can, this is another example. I want to say, if you want to see more examples from the model, we have a sample explorer up with lots of additional examples. You can find the link in the paper or the blog post we have on the Google Research blog. If you want to see more examples, including lots more mistakes. So there are mistakes, false positives, and correct answers. Okay, so let me summarize. So the main takeaway is that it turns out that training a large language model on a large corpus of math-focused data gives a model which has strong performance on math and science. And the second message is that inference time techniques with these models are very important, because you might train a model, evaluate it on some questions, get so-so or bad results, and think that the model can't actually solve questions like that. But with the right mix of techniques that we're still learning about, you can actually boost performance dramatically in many cases. And yeah, that's it. Thank you for listening.
Thank you. It's really, really great. It's really amazing work on many of these large language model works, but one which particularly the subject of new technologies in mathematics is certainly an incredible example. Questions from the audience?
Hi, sorry.
Yeah.
Yeah, sorry. So I just want to clarify on your few shot prompting. So does that involve few shots of every single category of the questions? Like, for example, it would be amazing to me that, you know, it still answers, say, the type of question that involving the constant G, right? Even if it hasn't seen it before, right? That definitely has seen it. And
oh no, there's no G in the prompt. No, the whole prompt for, yeah, I'll answer. So the whole prompt for, we have one prompt per data set. So one prompt for math, one prompt for MMLU, and the prompts, the questions in the prompt, it's 4 questions. That's all, that's the whole prompt, 4 questions, which were chosen randomly from the whole data set. So it's not even chosen by subtopic or anything, like there's no prompt for number theory.
okay.
Nothing like that. It's 4 math questions. You can see them in the paper. This is the first one. And then I just don't have space here, but there are 3 more just like this, chosen randomly. The only criterion was that we didn't want the examples to be too long, because then we run out of space for these. These models can see up to 2,000 tokens. So we want to leave some space there. So not too long answers. But other than that, we just chose 4 of them. We actually tried prompting with questions from the subtopic, for example, and that didn't help at all. Like, this is good enough, and it's hard. It was hard for us to improve on this, actually, by being more careful about choosing questions on the prompt. I can tell you there's even a paper on which claims that you can take prompts like this and change numbers to introduce mistakes, and that doesn't matter either. So it's not like, it doesn't seem to be the case that the model is actually learning from the prompt. It's more like it's putting it in the right mode or something, or to figure out.
But like the archive papers, you were fine tuning this model. Like what do they look like? They're just like that should be like high level math and physics published on archive, right?
It's the archive papers. It's all of archive. Yeah.
It's all okay. That's
It's
totally
all of
amazing.
the whole archive.
Okay.
Yeah. It's the whole archive.
Okay.
Yeah.
Yeah, sorry. Yeah, I think this is an important point I don't want to miss. So
yeah.
I see.
But,
okay.
But of course it's seen G before in fine tuning, probably in many web pages and papers. So it's not,
yes.
It shouldn't be surprising that it can recall the value of G, because that is something that has probably appeared in the training data set.
But I think maybe you can also test it on like even higher level math, right? Because if you train it on the archive papers, then it might be able to solve. I mean, that's the slide you were talking about, the ability that you haven't seen. Maybe it's able to do some even crazy math problems.
Yes. That's, yeah, definitely. I would say one thing is that, well, you see these benchmarks. These benchmarks, until recently, were considered extremely hard, because you see even the best published results and Google's best general language models just did like around 10% in these. And so we don't actually have data sets out there that are, you know, as well put together as math and MMLU that we can just go and evaluate on, because nobody bothered creating them because models were not good enough. So that's kind of part of what's taking time to make progress in this line of research, is that now we need to go and create harder math benchmark data sets to get a good signal of how good the model is. We just don't have these benchmarks because nobody created them.
Yeah, thanks a lot. I wanted to, yeah, I guess I'll let other people speak. But
More audience questions? I'll ask one. It's a tiny bit more technical. So, I mean, this process of the generating and doing majority voting seems very generally used. And so to what extent has there been, I know there's been work on doing it efficiently, and that was, for example, a big ingredient of the alpha code. But is there also perhaps theoretical work on trying to characterize, what is that doing? Is there perhaps another form of model that would automatically do that,
So I mean, I think that the reason this works has to do with the diversity of the incorrect answers, basically, right? It's like you have one correct answer, but you have several, sometimes lots of ways to make mistakes. And so that's kind of why this works, right? So even if I don't know, like 22% of the answers are correct and 78% are incorrect, but they're like each one gives a different incorrect answer, then you'll get a boost in the signal. And so there is basically what's going on here, and we did this experiment of figuring out what is the optimal temperature. So if you're sampling once, the best temperature is 0. But if you're sampling multiple times, there's going to be an optimal temperature. And doing majority voting, there's going to be a non-zero optimal temperature. And you can clearly see a trade-off where we calculated the accuracy of the model, just the probability that it gives the final correct answer, and that goes down with temperature. And we calculate the entropy in the space of incorrect answers, right? And that goes up with temperature. And so once you combine these, you get this optimal value for the temperature after you do majority voting. So the reason it works is simple, I would say. It's kind of clear why this works. Now the question of, well, pushing
is that
models.
data, is that data in your paper, or the graph?
No, I don't think we put this in. Yeah, I don't think we put this in the paper, but I can share the plots. These are just, if you're interested, I'm happy to share those plots.
Okay.
These were experiments. Sorry?
Yeah, but then this question, perhaps there's some better way to think about it, analogous to the role of Bayesian statistics and considering uncertainty and parameters. It's just analogous. It's not that, but perhaps some better way to think about the sampling so that you either don't have to sample or you can be more systematic.
Absolutely. I can say, I mean, you can see in papers, there's a lot of work on improving sampling from these models. So for example, another idea is, I mean, this is very common in machine learning, is like, if we have a few tricks that work, let's just throw a model in that will learn how to do it, right? Instead of trying to figure out from first principles how to do it better. And so you can try to train these verifier models to try and figure out if there's a mistake or not, right? And that's another line of research. So there's definitely, we're definitely in early stages of understanding how to better sample from these models. There's work on RL fine-tuning these models from human feedback. There's a lot of activity in being better at sampling from these models. And the advances that you mentioned for AlphaCode, that's good, not just for majority voting. It's just, of course, we want to sample from these models faster because they're pretty slow. You have to sample token by token. It's very slow. So there's more, like, I would say, maybe engineering work on that all the time. Specifically on how to get the model to kind of automatically do the majority voting, that I don't know how to do. I don't have an idea how to do that. But maybe that's the way to continue. I don't know.
Okay. Another slightly technical question. Have you studied the robustness in the sense that you rephrase the question and you make little changes that preserve the meaning, and does it reliably, if it can answer one form of the question, does it reliably answer the similar, the other forms?
Yeah, we did that. I would say not too extensively, but we did do this. We looked at. So these are the results for that. This is in the paper. Yeah, we changed phrasing for like I think like 20 questions. Every dot here is a question, and we changed numbers, and we saw that. I mean, there's no clear trend, I would say, of things. Like, sometimes it was better, sometimes worse. So it didn't matter much on average, let's say it like that. Yeah.
Let me suggest an amusing experiment that I did for GPT-3, which was in trying to think about what it's doing, what does it even know a number is? And so you can ask it, like, what's a random, pick a random number, random number between N and M, and 1 in 1,000, say, and it will tell you one. then pick another random number, and just keep doing this, and you can get some sense of what it thinks are the numbers, or at least the likely numbers.
Mm-hmm. Oh, that's nice.
There's some hand experiments like that.
Oh, what did you find?
Yeah.
What's the distribution?
Well, I have the output. It's not numbers that you might have guessed. It's easy to ask a question that will make it produce 42, but if you just ask it, for this type of random number, it starts off seemingly random, and eventually it does degenerate into things that are not random at all. But I have examples of that for GPT-3. Another very broad, and there starts to be interesting work on this, of course, in the big question of how does it do it? What is the thing actually learning? And so you could, of course, ask just for the decimal arithmetic. What is it learning? Is it learning some sort of a circuit to do arithmetic? Is it learning something else? And I don't know. Do you have any insights or work in progress on that, or you can share?
Yeah, no, not. I don't have any insights to share. Yeah. Okay. I hope we can figure this out. This question has come up a lot in discussions and in the team. I don't have anything to share on that. I agree. It's very interesting to try and figure that out.
So you haven't talked about the limitations of this method, right? Like, presumably the limitations of this includes the limitations of just transformers training on large data set, but specifically what's the limitation of this on the math data set, for example?
Yeah, I'd say the main limitation is that we don't have any automatic way to verify if what we got is correct or not. That's really the thing is we get what we get. We can try to push performance to be better with these tricks that we do in inference time, or make the model bigger, or collect more data, but there's no underlying formal structure here that the model is using that we could use to verify, or let's say, okay, so one thing is we can't automatically verify anything. So we don't know if the answer was right or not. We can check if we know the correct answer, we can check and calculate accuracies like we did. But if it's a new question, we don't know if it's right or wrong. And I can tell you after inspecting hundreds of examples from this model that the questions are not trivial. And so sometimes it can take like minutes or longer to even figure out if what the model did make sense or not, or find the mistakes, or it just gets harder and harder to do this manually even. That's one problem. Another problem is, let's say that we identify some area where the model is deficient, right? Like we did, we figured out that like, oh, look, like half the mistakes more or less are calculation mistakes. We don't have good tools of addressing that. Like you could say, oh, okay, so like connect it to a calculator or something to help it do the calculations. But we're fairly limited in like how would we do that if we start with a model that's generally trained on lots of data? How do we hook it up to a calculator and get it to learn to use that calculator? We don't know how to do that. It's not like a person where you can go and like explain to them what's going on and these are the mistakes you made. There's nothing like that. So scale works, but we can keep scaling up, but we don't have that much control over improving particular things, or we can always try to fine tune, but then we need to collect the data and so on. There's no easy way to do it. There's that verifying that to me is like the main limitation of this compared to like you can think of theorem proving approaches where you have the whole formal structure at hand and you can tweak it and manipulate it as much as you want. So that's very different.
Yeah, but I think that's exactly what I meant by this is the same limitations as the generative model of the foundation models, like because it's using natural language. What do you expect, right? Like there's no formal, and also what's amazing to me is that the mistakes it makes sense that that's a student who just doesn't understand the formal, reasoning of math that would make. I think some of the mistakes, it looks similar, like, okay, it actually doesn't understand the intrinsic thing, just trying to imitate. So it's an imitation, right? And I think that's in some sense, that's not super surprising. And it's where natural language can take it, right? I think that's kind of my interpretation of this.
Yeah, I totally agree with that. And indeed, the mistakes are very interpretable. That is nice. But yeah, just like you said, and I mean, you would see that. I mean, it's true for all of these generative models, just like in the party example. So, you know, this is an example where everything worked fine, where it turns out that scale solves the problems of the smaller model. So here, it turns out that scale solves the fact that the text is garbled, right? But what if there are some other problems that scale doesn't end up solving? Then what do we do? That's where things get harder. So we have this hammer now. We have the scale hammer, and some things are nails, but some things are not nails, and we don't even know like what's a nail and what's not a nail, right? Like what's going to be solved by scale, what's not going to be solved by scale. So in this sense, I completely agree. It shares the same limitations as these other generative models.
Another related problem, I've heard that if you try to get a model to not produce the correct answer, but to evaluate a candidate answer as to whether it is correctly reasoned or incorrectly reasoned, that is much harder and has not been achieved really at this level.
Yeah, so exactly. That's what when I mentioned the verifier work on these models that try to evaluate.
So you could imagine verifying natural language, and for whatever, either it just hasn't been solved yet, or it is a harder problem.
Yeah, it's something that there is a paper from OpenAI on doing this on basically on math word problems. So like elementary school level word problems, and you can try to apply it further. But yeah, indeed, it's not been solved. It might end up working, but so far it's not been solved. Yeah.
Okay, more questions from the audience, or see how time it is, because again, this is really, I guess we have a few more minutes, don't we? I mean, other than the scaling, I mean, scaling might be the best way to attack problems. Scaling might be a good way, but not necessarily the best way. And so then one could either try to extend a task or have co-training different tasks, or one could try to modify the architecture, of course. I mean, now this is starting to get very open-ended, but do you have any, I don't know, intuitions for maybe points that are missing that you could imagine improving through the architecture, or by training on other tasks? So I suppose if there were success, again, it's not the case. If there were success on this ability to determine whether a solution was correctly reasoned or incorrectly reasoned, then obviously it would be useful to co-train on that, as well as language and the rest, and then solve problems. But there might be other, of course, tasks that could contribute to problem solving.
Yes, I think at least to me, figuring out ways of introducing this formal structure would, it seems like a natural next step to me.
Right.
But it's not clear that you actually need to do that by changing the architecture. There may be easier ways. There may be easier ways to do this that kind of more play to the strengths of the model. But we haven't figured it out yet. But I think, I'm saying, like, basically trying to address the deficiencies that I mentioned by actually by actually trying to connect the model to tools or formal structure or something like that.
Right.
Would be nice. And this is something people are definitely working on. Yeah. But what I'm trying to say is, like, I think maybe one thing that I'm at least repeatedly surprised about is how much progress we can make without touching the architecture at all.
Yes,
There are all
yes.
kinds of ways of interacting with this model, with these models, where you can make meaningful improvement and you don't need to touch the architecture. And it's like the most tempting thing is to go, oh, let's go and put a formal structure in there. But actually, maybe there are easier ways to do it.
Yeah, no, I agree. That's definitely been the great progress of the last couple of years, is just running with the language model as it is. Yeah.
Yeah.
Yeah, I'm wondering, like, maybe if you have a data set of like training this thing purely on, say, like lecture notes. So the reason I think about this is because, like, you know, there you have like clear definitions, theorems, proofs, and maybe they'll kind of like give you a good representation of the formal mathematical reasoning. I'm not sure, you know, I'm just purely thinking out loud.
Yes, I mean I mean, it's of course, if there's a large source of kind of high quality data, it might push it more in that direction. My sense is that it won't. I don't know. I wouldn't bet that a formal understanding would kind of emerge from something like that. So like maybe it will improve things quantitatively, but I wouldn't bet on that, like solving the problem, like,
oh, that's interesting.
Getting them all.
So you don't think that just like this way of continuing, just like purely by choosing a good data set is not going to give you emergence of like formal understanding in the language model?
You know, I mean,
yeah, because that's interesting. Yeah,
I don't think so. That's my personal opinion, but I also didn't think that this would that this approach would work. I was pretty skeptical before we saw the results that this would do as well as it did. So I've been wrong before. So I don't really know, but I wouldn't bet on it. No. But that's pure speculation. Like, I don't actually know until we do experiments. We won't really know.
Another natural thing one could try would be questions where it's not likely you could solve the question without an additional fact or at least a hint, and then putting that with the question. And then this starts to be, you know, of course, a standard technique in question answering where you have retrieval and you supplement the question with relevant facts. Have you thought about the analog of that? Yeah.
I mean, of course, yes, there's a lot of work on and papers out on adding retrieval to models. I think in our context, it's not as, you know, the basic facts. I mean, this model has memorized G on Earth. I've also tried it on Mars. It knows G on Mars. It knows a lot of concepts.
Well, have you tried asking it any questions about details of string theory or quantum field theory? I suspect you would find that it had no idea what you were talking about. We can try it. We did try with Paul Ginsburg asking it what was the best candidate extension of the standard model, and it did say supersymmetry. This is GPT-3, that of course, not your system, but it knows something. But I think once you get into the more specialized areas, it's
yes, but then the challenge will be how to design a retrieval system that actually gives you an answer to that, because it's probably not written down that way I mean, depends on the question. It's not necessarily just written down in a sentence in a paper, right? It's more about
right. That's right. There are many questions where you would have to do some, you know, there would be relevant facts and perhaps some level of deduction. And
yeah, I think, to me, like, at least one way I like thinking about these things is, okay, we can try and build a system to do that, but why are we hoping that this will actually be any better than the model we have now? The best hope to have improvement is to give better data. Because if we're just doing different model with the same data that we trained the model on already, why didn't the model learn this?
Well, I think there are clear arguments in the other direction. Maybe we should have a longer discussion, you know, in a different context. I mean, again, I think the level of question you're giving it, it will see similar problems and answers discussed, many thousands, if not millions of times. Whereas if you ask it a more specific question about a 6-dimensional manifold or about a quantum field theory, there may be 10 papers that discuss that. And of course, a human can learn from one example in principle, but is it able to do that? I mean,
fair enough. I mean, we do know that these models are very good at, it's a very crude measurement, but the models are very good at memorizing. And bigger models memorize facts faster. So like if you have a small model, it needed to see a fact 20 times to memorize it. A bigger model might only have to see it twice to memorize it. So
maybe a follow-up would be to now pick a much more specialized domain of mathematics and focus the training on that.
Yes, I would say again, one limitation here is the evaluation, because we don't have a good benchmark for evaluating performance. And so part of the work is, well, we need to go and collect a benchmark like this. And so
we could. I think mathematicians or physicists could make such a benchmark if it's of interest.
If a benchmark is available, it's fairly easy for us to, if it's high quality, something like that, we would go and evaluate it. Yeah.
Okay.
When do you predict that scientists and mathematicians are out of jobs?
I refuse to answer. I don't think it's going to be soon, but I don't know.
It might surprise us.
It might surprise us, but I think these things will, my guess is, I mean, these things can probably be made to be useful assistants before they actually replace anybody. That's kind of what we're trying, that's more what we're aiming for, like trying to build, useful tools out of these things like people are doing with code. That would be really nice. And for sure that will happen first. I think there's no, yeah.
Okay, more discussion, more. Okay, well, if not, well, let's thank Guy again for a really very, very interesting, thought-provoking talk. And so we will not have a seminar next week, but in 2 weeks we will have Antonia Cresswell from DMind, who will in fact talk about question answering using a combination of a retrieval and language models and other techniques. So I hope to see you all there. Thanks for attending, and thanks, Guy.
Thank you.